Welcome back to you all. Today we are going to start our sixth unit. In this first we'll study about converters. Okay, these converters, the kind of converter we are going to study, will help you in connecting analog world with digital. So first let's try to understand the need of these converters. Let's say I wanted to store my information, my voice. Okay, so my voice is an analog signal and natural signals are analog in nature. Now in order to store my voice in this mobile phone, mobile will accept or store the information in the form of digital only. So how I can store my voice in this mobile phone? For that I need a converter which can convert that analog signal into digital so that my mobile can store this information, and if I want to further share this information, then I will be able to share that. But now let's say I have shared this information with you, the signal, the information what I have stored in my digital device. I want to give access to that information to you also. So in order to make it understandable for you, you have to convert that digital signal into analog again. Okay, for that we need a DAC or digital to analog converter. Okay, so once you have converted that into analog, then only you will be able to understand my voice or whatever I am saying. So this give reason why we are going to study about analog to digital or digital to analog converter. You may consider this as my voice signal what I am recording here. It is analog in nature, but in order to store this or process this, I have converted this into form of bits, that is 0101 also. And if you want to reconstruct or if you want to have access of that signal, if you want to hear that signal, my voice, then again you have to convert it into analog signal. Okay, then only you will be able to understand. So ADC is used to convert analog to digital and DAC is used to convert digital to analog. Okay, now in this graph I have tried to discuss something very important related to this. In the first graph, that is representing your this graph is representing your analog signal. Okay, see, this is your analog signal, and in this every time instance is defined. See, the value of the signal is defined at every time instance. Here in the next graph what I have did, the next this is representing your uh, discrete signal. Okay, here I have discretized the time scale. So rather having the value of this signal at every instance of time, what I have did, I have chosen certain levels and I will choose samples at these levels only. That's all. Okay, so once I have discretized the time scale, okay, what next step what we are going to do, we are going to quantize this. Okay, see here, what do I mean by quantization? By quantization I mean that I will choose certain levels. I have chosen these 4 levels in this case. Okay, and I will give value or assign value of this signal corresponding to these levels only. Okay, now I won't say that at time 1 is equal to time t is equal to 1, my signal has got any value like 3 volt or something. Okay, what I will say, that my signal is, or whatever, I will represent my signal in the form of these levels only. I will say that the value of my signal is either 00 or 01 or 10 or 11. That's all. Okay, so here I have used 2 bits quantization, so total different levels I can have is 2 raised power 2, that is 4. So I will use these 4 levels only for representing my signal. So let's say at time t is equal to 1, this value is corresponding to which level? Level 10. So what I will say, that at time t is equal to 1, my signal was having level 10. Okay, so as you can see here, we are making some certain approximation. I am not assigning that certain value to my signal. Okay, this is something, you can say, a drawback of a digital system. But similarly, you will proceed further, and for time t is equal to 1, I have assigned level 10, so I have represented by 10. At time 2 is t is equal to 2, it is somewhere approximately near to level 1 so I have represented by that level. Similarly you will complete the signal, and based on that samples or levels you have received, you will reconstruct the signal. This is representing the signal what you have reconstructed. Okay, and what was the original signal? So if you this is your original signal. Okay, so you can see the difference. Actually, these are representing the difference or limitation of digital signal. What I have actually transmitted, I am not able to reconstruct that or actual signal. So what we can do in order to improve the performance? For improving that, what if I have chosen few more levels? If I have chosen few more levels, let's say, so here I would have got 8 different levels. So now here I have 8 different levels. So if I am having 8 different levels, so I can represent my signal, or that approximation will be more fine, and that will help us in reconstructing the original signal in a better way. Okay, so as a concluding remark, we can say that for if we are having more number of levels, see, we can say that the more number of levels, the more better will be the reconstruction of the signal, and hence its representation. See, with the help of this image, in the first image I have used only 2 bits. Okay, so total number of different levels were 2 raised power 2, that is 4. So this is barely understandable what is inside this image. Okay, as I have increased the levels, see, I keep on increasing the levels, the clarity of image has increased. Here I am using 100 different levels, 100 cross 100 different levels. Okay, so the clarity of image is very good. So what I mean to say with the help of this discussion, that the more number of levels you will have, the more your image or the presentation of data will be clear. Okay, and there is one more important things, like if I am having more number of levels, then the difference between two consecutive levels will be very low. Okay, so that difference between two consecutive levels is known as step size. Okay, that is responsible for one change in LSB. Okay, we'll understand that a little further in the next slides. See, so here that the quality what we have discussed is mean we are going to talk about a quantitative measure of that quality, and that is represented with the help of resolution. Okay, and it is defined as how finally output of any DAC or ADC may change between discrete binary step. These are the formula for calculating the resolution. These will be very helpful for certain numericals, so you can go through this. Full scale range divided by 2 raised power n, where n is representing the number of bits. Let's say if I am using 2-bit quantization, then the total number of bits will be 2. If I'm using 3-bit quantization, then the number of bits will be 3, and so on. Okay, and these full scale range, V max minus V in and V reference are almost same quantities but represented differently in some cases. That is why I have represented 3 different formulas. Okay, so now let's talk about the basic concept of digital to analog conversion. Having studied about the basic concept of converters, now we are going to talk about basic concept of digital to analog converter. Okay, so first in order to proceed further, let's first try to understand how we convert any binary number into digital. Okay, not digital, sorry, in decimal. So let's say I have got this binary number. In order to convert it into decimal, what I will do, I will multiply these these numbers with the corresponding weights. So what is the weight at this position? It is 2 raised power 0 and so on, 2 raised power 1, 2 raised power 2. So I have multiplied, these are the weights, and I have multiplied with these values. So 0 multiplied by 1, that will be 1 0, that is why I have written 0. And finally what you have to do, you have accumulated that. Okay, and that has given you the decimal value. So the same kind of concept we are going to use for converting any digital signal into analog. We will convert them into a corresponding decimal signal or voltage level. That voltage level will represent the corresponding uh, analog value. Okay, so will represent a generalized formula for that conversion. See, this is representing the generalized formula for that conversion. And if by any mean we can design a circuit which is capable of producing this kind of output, okay, we can solve the purpose. Yeah. So let's have a look on this kind of circuit. This is the kind of circuit we have. So here I have used these resistors. Here I have used these resistors, and these are arranged in the form of binary weights. See, what is the weight of this? It is having R only, mean you can say it is 2 raised power 0, 2 raised power 1, 2 raised power 4, 2 raised power 2, and 2 raised power 3. Okay, here let's say I have got, and this is your this is your op-amp. Okay, you all are familiar with this, I hope so. And these are your resistors, these are the switches. Okay, and this is representing the ground level, and this is representing the, see, this is representing the voltage reference. Okay, so now let's say if you want to convert, let me erase this now. Let's say you want to convert this 1 0 1 0. Let's start from beginning. Okay, let's say you have to start, or you have to convert this information 1 0 1 0 in the into an analog signal. Okay, so according to the signal, if it is 1, then these resistors will keep on connecting with V reference. But if the value is 0, if the value of 0 is 0, then these resistors will be connected with the ground. See, with the help of animation, this was 0, so I have connected it with ground. This is also 0, the last bit is also 0, so I will again connect it with the ground. Okay, so that is how, if I have got, let's say 1 1 1 1, then all the bits will be connected with the V reference. If I have got all 0 0 0, then all will be connected with 0 0 0 only. Okay, so once I have did that, now this op-amp is represented in the, or in the summing, in the form of summing amplifier, if you remember. Okay, so what would be the output of a summing amplifier? This is the output of summing amplifier actually. This is the output of a summing amplifier. So you don't have to do much calculation or worry about anything else. All you have to do is to put these values. See what we have got: 1 0 1 0, and 1 is your MSB and 0 is your LSB. So I have placed those values according to that in this formula, and we'll solve. If the rest of the values are given to us, we will solve this and we'll find the corresponding V out. That's all about this first kind of digital to analog converter. It is known as binary weighted DAC. Okay, so I hope the operation is clear to all. In the next lecture I will further explain this.